So I guess I'll also start my talk with a bit of a caveat. So this is very recent work. It says, with thanks to the Simons Institute. So over the summer, I was visiting the Simons Institute at Berkeley, where they had a program on deep learning. And really, the reason I was there was because one of my very close friends, Matus Telgarsky, was one of the organizers. And I told him when he invited me that I didn't really do any deep learning, and he's like, okay, well, you can get started. So this was sort of mentally like a summer internship. And what you see now, well, it's August. So this is like the report on what I did. So this is kind of still in progress. I'm not really sure when we'll be done with the paper. So I apologize if some of the ideas or equations are permuted, because that's kind of how it still is in my head. This is joint work with my colleague and collaborator, Varun Zog, who is in ECE at Madison. Okay, so there's this, so as we know, neural networks are very accurate. So you feed in lots of training data, and they classify very, very accurately on test data. But there's a phenomenon that was observed several years ago and has drawn a lot of attention, particularly in the theoretical community. And it's a curious property of neural networks that even though they classify very well, let's say to 95+% accuracy, what happens is that if you take a neural network that is trained to classify images very accurately, and you choose some sort of adversarial tweak to the image. So in this case, this is a panda that was classified accurately. And then you choose some very small perturbation. So the magnitude of each pixel is perturbed by at most epsilon. And you choose that perturbation correctly. Then you can make the classification incorrect. So there's another animal called a gibbon, and you feed this new image, which basically looks just like the panda image, into your neural network, and it will fool the neural network. So the neural network will decide that this is something different. And this is a problem because in practice, people like to use neural networks to classify images, and they want to do better than humans. And even though they might do a little bit better than humans on so-called clean images, the problem is that if you choose these adversarial attacks, then you can sort of hack the network and make it predict incorrectly. And this is bad if you have an application in security or medical imaging or something like that, and you want it to be more robust. So I've been quite fascinated with this property for a while when I first heard about it. And there are various methods that people have for trying to deal with this. So in my head, to kind of sort out what this phenomenon is actually referring to, I like to think of a classification boundary. So imagine that you have images of one type. Let's say the pandas are over here and the gibbons are over there. And what your neural network is doing is it's creating a decision boundary that's classifying very well. So in this case, it's 100% accurate on all of the training images. And in fact, if you populate it with some test images, then they probably will also do very well. At least that's the way that we see the experiments going in actual applications. But the issue, so what's going on here is that even though things are classifying correctly, somehow the neural network is, in a way that we don't quite understand, creating the classification boundary so it's really, really close to the images that we feed in. So I call this sort of a conservative predictor. So it's creating the correct classification boundary, but there are lots of correct boundaries it could be drawing that separate the pluses from the zeros. And it's separating things in such a way that you get really, really close. So if you choose some sort of perturbation, let's say to this red circle, then even though it's classified correctly, you can just perturb it by a tiny bit and go over the line. And so this is what neural networks are doing. So there are a couple methods that people use to try to combat this. One of them is known as data augmentation, and the first reference I found of this was from analysis of text, actually. There may be other references before that. So the idea is that you still have the original red and blue points, but you kind of tell your neural network, I don't want to just classify these images correctly, but I want to classify them and some ball around them correctly. And so what I'm drawing here is I'm drawing some sort of enlargement. So you can imagine a dotted circle around each of these points, and to say that everything that is red plus dotted has to be on one side, and everything that's blue plus dotted has to be on the other side. And so maybe then the neural network will classify like this, and you'll get this green line. Okay? So the problem with this, of course, is that theoretically it sort of makes sense. But then now imagine that you're in a high-dimensional image space, and you want to, so data augmentation means that you introduce some other examples that are close by. So it's like you take not only this red image, but you create lots and lots of perturbations. Okay, but the problem is that you need sort of infinitely many, or a large number of perturbations, because you're in a very high-dimensional image space. Your dimensionality is the number of pixels in your image, which could be very, very large. So it's not really that practical to say, let me just protect every point by lots and lots and lots of points. There's another method that is quite popular, and that's called adversarial training. And there are different ways to think about what adversarial training is doing. But one way to think about it is to say, OK, so we don't really need to protect this point by all the points in this solid ball. You know, maybe we just need to add on some other perturbations that are like kind of going in the right direction. So we make sure that that point is classified correctly, and then some appropriate points are classified correctly that push the black boundary to the green boundary to get what we want. A very popular method for constructing these adversarial perturbations is called the fast gradient sign method, or FGSM. I don't want to go into too much detail about this, but the idea is you take your point, let's say it's the red point, and then you add the correct direction of the perturbation. And it turns out that what has been sort of suggested in papers and kind of works somewhat well is where you look at the gradient of your loss function. Why does this make sense? Because, well, the loss function is kind of indicating how close you are to the boundary, right? So the loss is going to be pretty small if you're far away, and then it's going to be bigger if you're close by. And so you want to kind of go in the direction of the boundary. So the gradient of the loss will tell you what's that direction in which things are going to change very quickly. It turns out that this sort of protects against what are called L-infinity perturbations, whereas there are maybe L2 perturbations or different sort of distances. Okay, so the idea is that, you know, it's sort of like impossible to decide based on your training data exactly what the worst case perturbation is. But this fast gradient sign method is one way of creating an image that seems to be going towards the decision boundary, which seems to improve the robustness of your classifier. It's called fast gradient sign method because it's very fast to compute, and it's a sign method because you're basically looking at the vector of the gradient and just going epsilon perturbation, either plus or minus. The other thing I want to point out, which is why I wrote this down, is that it turns out that this is very easy to compute from a trained neural network. Okay, so when you think about optimizing things, you usually think about optimizing your loss with respect to the parameters, which are theta. So it wouldn't be too unrealistic to imagine that, you know, if I were talking about taking a gradient of a loss with respect to theta, then that should be easy to do with a neural network, because a neural network is doing gradient descent anyway. But one thing I want you to keep in mind for later is that actually neural networks can also take derivatives with respect to x, your input. Okay, so this is kind of weird when you think about it as optimization. But when you think about what a neural network is doing, well, on the first layer in the inputs, it's sort of taking your weights, let's say theta, and it's doing transpose with x, which is your input. And it does something to that. So from the point of view of what the neural network is computing and storing, it can also tell you, in addition to the gradient with respect to theta, what the gradient is with respect to x of the loss function, or it turns out the parameters and so on. And this is one thought that I want you to hold on to for later. Okay. So I guess this is what I'm saying here. Then it turns out that we can actually take these gradients efficiently when we have a trained neural network. There's another method that I want to point out because I spent a lot of time thinking about this earlier in the summer. This is another method for trying to make neural networks more robust. It's called randomized smoothing. So basically the idea is that if you look at just the first image on the left, well, if you smoothed out somehow the decision boundary, made it like a straight line, then maybe that would be more robust. And so randomized smoothing is kind of a way of appropriately preprocessing your data or convolving it with some kind of Gaussian, which will in the end smooth out your decision boundary. Okay. But then the issue when you start thinking about these methods is that there's a little bit of an inherent trade-off between robustness and accuracy. Okay, so what do we mean by robustness? Well, robustness means that if I have a classifier and I perturb the input by a little bit, the classifier shouldn't change too much. So if you think about looking at the panda and the gibbon, right? I mean, I have these two input images which look really, really close. That's in the, let's say, xi is the panda, x prime is the gibbon. They look really close. And I want that the classification is going to be the same. So I want that to be true of my classifier. On the other hand, I also want my method to be accurate. And so what you see if you start looking at these images is, well, okay, if I kind of straightened out this line, then maybe that would be more robust in some weird way that I need to quantify. But at the same time, you know, the images that actually are sort of on the curvy, close to the curvy boundary are going to be misclassified. And this is what happens when you try to apply some of these methods. I think I put an image of this. So I took the same images as before, and I said, well, what if we try to do some data augmentation and we enlarge things by, this is supposed to be a big radius, okay? So we kind of want to protect all of these points. And then really the green line doesn't have many choices anymore. It has to follow whatever curvature is going on here. But who am I to say that this is the right classifier, right? This is just a method that I use to try to protect these points. And so we see that as we try to become more robust, as we try to increase these balls and protect against perturbations in these balls, then the boundary might become further and further away from what actually is supposed to be the case based on the data generating distribution. Okay. So then I started thinking, well, how do we quantify this? So I spent a lot of time trying to figure out if there were fundamental trade-offs between robustness and accuracy, and I didn't get very far. Okay, so there's something else that I started thinking about instead. And the idea is, instead of claiming that there is a fundamental trade-off between robustness and accuracy of any classifier, what if we try to design some classifiers that are inherently more robust? And the way we do this is we look at the features that we're using to base our predictions on. Okay, so there's this image that I want to look at for a little while. So what we have here is we have a mixture of Gaussians. And these are a mixture of very flat Gaussians. So the covariance in the horizontal direction is much bigger than the covariance in the vertical direction. Now, if I told you that I wanted a good classifier, that I didn't care about robustness, then what would you do? Well, you would look at something like this. Let's say maximum likelihood classification in logistic regression. Okay? And so another way to think about it is that logistic regression is learning a parameter vector beta. In this case, it's two-dimensional. And it's trying to project things onto the beta direction. So really, the beta direction is perpendicular to this. So it's projecting things onto that direction, and then it's classifying. Okay. But my claim is that if we don't just care about prediction accuracy, and we care about robustness, whatever that means, what we should be doing is doing something like this. Okay, so this image, or some version thereof, is in a paper on neural networks, and it took me a while to understand what was going on, because this just looks like a terrible classifier, right? Okay, but now, in terms of robustness, so we go back to this first image, and my claim is that it's not a very robust classifier. Because what we cared about is how much I should perturb points in order to put them over the boundary. And so we see that even though this is a great classifier, most of the points are really close to the boundary, right? Pretty much like all of them, because I chose these two blobs so that they were basically kind of like parallel point clouds to this boundary. On the other hand, if I look at this classifier, then I see that, okay, there's some points that are now misclassified. On the other hand, since these are Gaussian clouds, the bulk of the mass is sort of in the middle of the red cloud. And the bulk of the mass here is in the middle of the blue cloud. And now how far do I need to move those points to put them over the boundary? And so you'll see that it's something sort of non-trivial, right? Whereas here it's sort of trivial. You just move points by a tiny bit, and they go over the boundary. Here what we see is that you move some points, and even these are really far away, and they're kind of further from the boundary. Right? So the idea is that maybe, even though the most accurate vector I should be using for my prediction is the beta vector that corresponds to this classifier, you know, if I now want things to be both robust and accurate, then I should be basing my prediction on some other projection or some other feature. So you can think about xi transpose beta as a feature. If I were to extract a one-dimensional feature on which I want to do prediction, then which beta should I choose so that I do logistic regression using xi transpose beta? This is also an example that's worth mentioning, because I think this is what kind of made a splash in the deep learning community quite recently. This is another example, which is, it's kind of like this Gaussian point clouds example, but it's also showing that there are certain features that might be more robust than others. So the idea is that you again have a mixture. So you have yi, which is your label, and it's either plus or minus. So imagine that that's like my two Gaussian clouds, okay? But they're not exactly Gaussians. So what's going on is that there's a feature which is sort of the robust feature. So this first feature is basically telling you, I mean, it's going to be +1 or -1, depending on what the class is. But then there's some uncertainty, so there's a flip, all right? And then the other features are sort of weak features. So they are going in the right direction in the sense that the means are correct, right? So if the class is +1, then these clouds are going to be centered at the all +1s vector with a little bit of noise. So the idea is that if you were to try to classify correctly, with the best accuracy, you should be using all of these features. So these features tell you a little bit, and this feature also tells you a little bit. On the other hand, if you choose this eta parameter to be very small, then that's kind of like saying that the distance to the boundary is really small. Okay, so we see that if you want to be robust, you actually shouldn't be using any of these features, and you should only be using the first one, which is the robust feature. Now, you have to think about it a little bit more. It really depends on the trade-off between how big Q is and how big eta is. But the point is that if you make eta sufficiently small, then really all these features are useful for prediction, but they're just not very robust. And so we see that one of the features comes out as being very robust, and the others are not so much. So the question again is, how do we do some sort of feature extraction that tells us that we should be picking this feature and not those? And then the trade-off between accuracy and robustness is that if I didn't care about robustness, I would use all the features. But if I do care about robustness, maybe I should rank my features in a certain way. Then there's another paper I want to mention as well, because I also found this quite fascinating. So this is a NeurIPS paper from last year. And the idea is that in order to try to build a more robust feature classifier, you should build a graph on your data and then look at your graph Laplacian. So again, without going into too much detail, so what I've done here is I've taken these points from the earlier picture right here, and I just dropped the decision boundary, and I said, well, let's construct some sort of a nearest neighbor graph. So you get a graph. And the idea with robustness is that you don't want your function to change too much for points that are close. And so because this graph is telling us where points are close, then we want to extract a function that takes on a different value for every one of these points, but doesn't change that much across edges in the graph. And these are ideas that have come out in spectral graph theory. You can talk about regularizing according to a graph. And so there are methods that have been proposed for doing robust feature extraction with respect to the graph that's placed over your data. All right. So the approach that we took was inspired by these works, but also took in a different idea. And so the idea was to use an information theoretic approach. Again, the goal is to figure out how to extract robust features. The question is, like, what should you use as your objective, and does it actually work? So there's a paper that's quite famous now because it's somewhat controversial. And this paper was by Tishby et al. The first version of it appeared in 1999. And it was known as the information bottleneck. So the idea here had nothing to do with robustness. The idea was that they wanted a method for extracting features. And these features should be good at predicting whatever the output is. So they should be good at predicting y. And they should also be very good at compression. So you don't want to be too redundant. Like if you just take all your inputs x, then those could be really good for predicting y. But maybe some of them are redundant. So you really just want to extract out some features t that are not so redundant for x, that still are good at predicting y. This was formulated in this information theoretic setting. So I refers to the mutual information between two variables. So remember, x is the input, y is the output, and t are the extracted features. And we want to impose that the features are conditionally independent of the outputs given the input, because the features are just extracted from the input. And what this formulation means is, well, the one thing you need to know about mutual information is that it's non-negative. And furthermore, when it's 0, that means that two variables are independent. Okay, so if you want things to be less independent, then this value should be bigger. All right, so what we want to do is we want to make I of tx small, and we want to make I of ty big. Right? And so basically it's saying that we want t and y to be very related, but then we want t and x to be not very related, because we're minimizing the mutual information between t and x, and small mutual information between t and x, like t and x being, the mutual information being 0 means that there's no relationship. Okay, so we want compression, we want small relationship between t and x, but we want to predict well, so we need good relationship between t and y. So this was known as mutual information bottleneck. And this is where things become a little bit controversial. So there were various studies, and especially with the new wave on deep learning, claiming that, in fact, deep learning, neural networks learn according to this mutual information bottleneck. So in this case, they were looking at features that were in a deep network. So you can imagine training your favorite neural network. It extracts features at each layer. Right? So just focus on a particular layer and ask, for this particular t, what happens if I compute what this objective function is? Okay, so the hope is that as I learn, things become more compressed and they predict well. So you would hope that somehow this objective function is going to be getting smaller and smaller because I'm doing some learning. So I'm trying to predict my features well, and I'm trying to predict my outputs well, and I'm also trying to do compression. And the authors went a little bit further than that to say that there are actually two different phases in neural network learning. And one is known as a memorization phase, and one is known as a compression phase. So first, you sort of learn to extract features. You recognize, for instance, the handwritten digits. So you recognize that there are certain properties of 0, 1, 2, up to 9. After that, you try to compress things. And without spending too much time on this slide, basically, the idea is that I of ty should be constantly increasing because you're getting better and better at predicting things. On the other hand, I of tx is first increasing and then decreasing. And this picture is taken from this paper by Schwartz, Ziv, and Tishby. And so you see that I of y, which is on the vertical axis, it's always increasing, whereas on the horizontal axis, these orange dots are sort of they're getting bigger, and then they're getting smaller. So what you see here is you see different layers in a neural network, and over 50 samples of random initialization. Now, this paper kind of, well, there was a follow-up paper at ICLR, maybe in 17 or 18, where they claimed that these simulations were sort of very carefully chosen, and this is not what happens in neural networks. And so if you Google the ICLR open review, you'll see that there's this war between the authors. So the follow-up paper got in, but these authors said that the reason why the simulations are different is because they don't know how to calculate their mutual information accurately from simulations. So we're not going to get into that, because that's not the point. The point is that we use this sort of as a starting point to try to extract robust features. Because, again, there's nothing to do with robustness here, right? It's just like we want features to be an accurate way to predict the labels, and then also be good for compression. OK, but before I move on, so another nice thing about this formulation, well, in general, it's kind of nasty, right? You want to optimize over all possible functions of your x's. But there was a paper that showed that at least when x and y are jointly Gaussian, you can actually characterize what the extracted features are. And the hope is that if things are jointly Gaussian and you can write down the exact formula for what the feature should be, hopefully it's something realistic. Hopefully it's something meaningful that you can actually, like in the Gaussian mixture case, plot the result and say, OK, it's doing the right thing. OK, so it was shown in this paper that, in fact, somewhat surprisingly perhaps, is that if you look at any function of your x's, it turns out that the best thing to do is a Gaussian mapping. So if you're allowed to extract any function of your x's through any nonlinear transformation or whatever, the best thing you can do is actually to look at Gaussians. All right, and then it was shown that the right projection has to do with eigenvalues and eigenvectors of the joint covariance matrix between the x's and the y's. OK. So what did we do? Well, we started thinking about how you can try to encourage robustness when you're creating a mapping from x's to t's. And what we ended up deciding on was a Fisher information term as a regularizer. So this Fisher information term might look a little bit weird from what you're used to seeing in statistics, but it does have this idea of a score function, right? The gradient of the log of the density. And normally what you have is you have the density as parameterized by a parameter. In this case, we're going to parameterize things by x. Because what is the Fisher information doing? It's telling us something about the curvature of a distribution of a density with respect to changes in a parameter. And now what we want is we want that if x changes a little bit, we don't want to change the distribution of t very much, right? Because we're trying to encourage stability of the t's. So we hope that if we look at the conditional distribution of t given x, small changes in x don't change the conditional density too much. And then the other stuff is just sort of an expectation, because in a Fisher information, you have an expectation. So we're taking an expectation with respect to x and with respect to t. So as I said here, in some sense, a smaller version of phi means that these gradients of the log of the conditional density aren't going to be very large, and therefore we should have some stability with respect to changes in x. Also, I should say that this is sort of on average. So earlier, I was motivating all of this by saying that we have these adversarial perturbations. And ideally, we want this method to actually be robust to adversarial perturbations. But for starters, if we're trying to extract some robust features, we're just going to look at average case analysis, because it's easier to compute things in that sense. OK, so this leads to the robust information bottleneck, as advertised in the title. So what you see here is you see, again, these I of tx and I of ty terms. And then there's going to be a parameter gamma that trades off the compression and the prediction. And then there's going to be another term, which is the regularizer, and that is this Fisher information. And you might ask a priori, well, why did you use Fisher information? It came out of nowhere. And really, the clean answer is that it turns out that in the Gaussian case, you can write down what the solution is to all of this. And that's why things become kind of clean with mutual information, and they also become clean if you add a Fisher information regularizer. There was another formulation that we also studied that we could also kind of analyze nicely. And this is where we sort of pulled away from this information bottleneck. Because really, we weren't starting with information bottleneck. We were sort of starting with how do you make things more robust? What sort of regularizer should you add? And it seemed like this Fisher information seems pretty reasonable, right? I mean, you change your x's by a bit, it doesn't change the distribution of t too much. So you can also think about other ways of trying to say that t is predicting y well. Because really, the regularizer is saying that the changing x doesn't change t too much. And then we want something that says that t is actually predictive for y. So you could imagine looking at a minimum mean squared error. So minimum mean squared error is really just saying, what is the best predictor that I could use as a function of t? And that's going to be expectation of y given t, and then the mean squared error of that. All right, and it turns out that you can kind of analyze these in similar ways, which I'll get to in a moment. So one comment is that, well, the MMSE method is potentially preferable if you're really looking at distances between inputs and outputs. So mutual information is kind of an abstract thing. It tells you how independent things are. But if you really want to measure prediction in terms of squared accuracy, then maybe MMSE is better. But that's kind of just a speculation. Another thing that's important to note, which is relevant for the computations, which I won't go into too much detail on, is that it turns out that these objective functions are invariant to scalings of t. And this is something that we liked, because you would hope that if you say that certain features are more robust, then if you scale them up by 100, they're still equally robust as if you didn't scale them up by 100. This becomes useful in our theory because what we'll show actually is that in these settings as well, in the Gaussian case, t should just be a linear transformation of the Gaussian. And then what we can do is we can rescale t so that the error term has identity covariance and just optimize over A. So this becomes a linear algebra problem. You can rescale your t and make your residuals just identity covariance. OK. A couple other things about this regularizer. So I sort of pulled it out of nowhere. As I said, it was motivated by the question of how sensitive is t, or the distribution of t, to perturbations in X. It turns out that it also has some nice properties, which fall out of some information-theoretic analysis. So you can think about the regularizer as a first-order approximation of changes in the mutual information. So it turns out, and this follows from a result in information geometry called de Bruyn's identity, that if you look at the mutual information between X and t, you perturb X by a little Gaussian. So you add an independent Gaussian noise, then you get the Fisher information as a first-order term. So this says, well, all right, if we want to make this small, then we want to make sure that the information content of X relative to t isn't too much if I perturb X, which is also consistent with what we were saying about robustness. Another nice property is that it turns out, and maybe don't stare at this too hard, is that if p is small, then in fact a certain KL distance is small. So the KL distance is between the conditional distribution of t given X and t given a perturbation of X. And so we can show that, in fact, KL perturbations are also small if phi is small. So these are just sort of justifications for why phi is sort of a nice thing to look at. And it turns out that, well, by Pinsker's inequality, if KL is small, then TV is small. If TV is small, then Wasserstein is also small. So a small version of phi is perhaps something that really should be desired. OK, a little bit more about this regularizer. Again, trying to convince you that it's a nice thing to do. So you could imagine different settings. One is where you're extracting your features in some linear way. So here, this is just a linear transformation of X plus Gaussian noise. X could be Gaussian. X could be a Gaussian mixture. It could be whatever you want. And it turns out that you can actually calculate what phi is, because phi is this Fisher information that depends on the conditional distribution of t given X. And you end up with basically the sum of the squares of the entries of A. And this also agrees with the intuition, because what happens is that we see that a small value of phi, so more robust features, corresponds to a small value of the norm of A. And that means low signal-to-noise ratio. And normally you think that low signal-to-noise ratio is a bad thing. But on the other hand, if you want things to be more robust, all right, so you want your t to not change too much, then what's the most robust thing you can do? Just generate independent features, right? I mean, that's like terrible for prediction, but it's really robust. And so we see that making the signal-to-noise ratio small is, in fact, what is encouraging robustness in features. Of course, we would not be choosing a tiny SNR because we have the other term, too, and that's either the MMSE or the information bottleneck term. So that's trying to give us good prediction in addition to robustness. You can play a similar game where you let your t be binary features. And if you look at binary features, then maybe these are parameterized by some logistic parameter, W, and you can try to calculate exactly what this phi term looks like. And it turns out that the phi term also depends in some sense on a signal-to-noise ratio. And then there are other terms that come from how confident your predictors are. So this is like p times 1 minus p. And we know that p times 1 minus p is minimized when you're at 0 or 1. So it's telling us that if we want to be very robust, then we want the predictions to be very confident. You're either very confidently positive or very confidently negative. OK. All right, so that's to convince you that phi is sort of a reasonable thing to look at. Then the next thing that we sort of looked at was, well, OK, so Well, we could say, let's just use this in practice. But before that, maybe let's try to look at the theory behind it. In a very special case, when we can actually understand what the joint distribution of x and y is, just like the information bottleneck, can we analyze what sort of features are extracted? And so that's what we did here. We looked at the case when x and y are jointly Gaussian random variables. And it turns out that you can also show, although it takes quite a bit of work, that the optimal choice of t is, again, a jointly Gaussian random variable. And maybe the very short summary is that it has to do with the fact that Gaussian random variables are maximizing entropy subject to a bound in the covariance. So you kind of want to look at your objective function and then move it around in such a way that you end up with a statement that says Gaussians are the best thing to do. Okay? So then the game becomes, as I said, look at t, which is some linear projection of x plus Gaussian noise. Assume that your Gaussian noise is standard normal, and then optimize over A. So then you do a lot of linear algebra. And it turns out that the linear algebra actually kind of works out. So this is the MMSE formulation. This was the MMSE of t as a predictor for y. So in Gaussians, you can easily write down what the conditionals are, expectation of y given t, and you can write down what your MMSE should be. So you get something like this, and then you move it around a bunch, and you end up with an answer that your projection matrix, so these are the directions in which you want to project x in, that presumably give you robust features. There's sort of two things that are going on. One is that, again, it has to do with eigenvectors of an appropriate matrix. Okay, so what this means is that if you have jointly Gaussian x's and y's, then hopefully the direction that you're projecting in that's predictive has to do with the covariance between x and y, because that tells you the shape of the distribution. And so what follows out of this is that you, again, have some eigenvectors of the proper covariance matrix, and then you also have a little bit of scaling truncation. And maybe I'm not going to go into detail on this, but let's just say that a similar type of result comes out if you analyze the information bottleneck itself without the phi term. And then what happens if you add the phi term to make things more robust is that you have a slightly different set of eigenvectors, and you have a slightly different set of scalings. And in particular, the scaling is a little bit of a truncation. So beta was this regularization parameter that said, how much do I care about robustness? And if beta gets gigantic, then what happens is that all of these d's become 0. All right, so basically what that's saying is that I had these eigenvectors, and I'm going to scale them by something, and I'm going to scale them all to 0. So basically, I'm just going to make my t independent noise all over again. Because I said if I make a 0, then I'm just generating independent noise. But of course, the more interesting case is when beta is set to be something in between. So I actually am doing something with prediction. I'm getting some notion of how predictive x is for y in certain directions, and then I'm truncating certain vectors as well. Okay. Similarly, you can analyze the mutual information formulation. I am not going to get into that, but in some sense, it has a similar flavor. So this had some d times u, and this also has some d times u. It's a different d and it's a different u. But the u comes from certain eigendirections as well, and the d is another scaling. And you can show that, in fact, larger beta also squashes things to 0. OK. But then there's something else. So now we believe that the Gaussian case is doing something reasonable, so therefore, maybe we should just go ahead and use this method. But then how do we actually use it, right? So we're in a setting where we have x's and we have y's. So I'll show you some preliminary results for MNIST data. So like really concrete, right? We actually have images and we actually have labels. And how do we go about extracting t, right? And so nobody would think that x and y are actually jointly Gaussian. So we go back to this sort of formulation and we say, well, how do we optimize this? So there's just absolutely no way you can do this for an arbitrary distribution of t as a function of x. Fortunately, there's some work in this direction that was done in the case of the information bottleneck. So remember, sort of from a philosophical point, what we've done is we've added a regularizer, right? So the information bottleneck itself just had the first two terms. And so this paper, which was an ICLR paper from 2017, said, OK, so great. People have shown theory for the Gaussian case, but how do I actually use this in practice? And so they came up with some variational method for hopefully extracting some reasonable features, where you just have the first two terms. The idea is, well, in variational inference, so there are usually a couple things that are going on. One is that you sort of restrict your search space into something that's more tractable. And another thing you do is you, if you're minimizing something, you upper bound some other function that's nicer, which is an upper bound for the function you're optimizing. Okay, so there are two things. One is that we're going to look at a certain class of functions and hope that we have meaningful features extracted from that. And the other thing we want to do is we want to come up with an appropriate upper bound of this kind of nasty objective that can be optimized appropriately. Now, I wish I could tell you that we had a convex function that upper bounds this and everything is great. Well, not quite. But the thing that we do have is we have some function that upper bounds this, which can be optimized efficiently using stochastic gradient descent. So stochastic gradient descent is a very big deal in neural networks because that's the only way that you can really attempt to optimize something where it's so complicated, there is such a high dimensionality of your parameter space, and tons of data. So whatever you're trying to do with neural networks, you have to be able to have some sort of stochastic gradient descent like minimization going on. And if I tell you to just try stochastic gradient descent on this objective, you'll say, like, what is that, right? I mean, it's not very easily written down as empirical risk of minimization. You can't just say, draw some of your samples and take a gradient step. OK. There's a related paper that I'll kind of touch on that is related to both this information bottleneck paper and also what we did. OK, so here's where it might get kind of confusing because it's sort of stepping through some language and some terms that might be a bit unfamiliar. So the idea is that we're going to train a neural network that extracts certain robust features. All right? So I said that we want to optimize just over a certain class of conditional distributions. Because we want to optimize over all possible transformations of x, and that's impossible. So let's just look at Gaussians. So we're not saying that x and y are jointly Gaussian. We're just saying that whatever features we're extracting are going to be a Gaussian function of the x's. And that can be parametrized using theta, where theta is going to be something with the weights of the neural network. So it's not as simple as saying theta transpose x. It's saying you have a neural network, and there are weights corresponding to all the layers, and somehow that's getting scrambled into everything, and you're extracting some features t. So what you really want is you want to train some encoder neural network, which is giving you these features. All right. But so how do we actually do this, right? Because that sounds great, but we need to somehow get back to this function. And I was saying that we need to come up with some surrogate function that can be optimized using stochastic gradient descent. All right, so let's focus on the phi term. So really, we need to come up with a bound for all three of the terms. If we focus on the phi term, then because of the nice parametric form that we're assuming for this feature extractor, right, this tells us what t given x looks like. And now we want to look at the Fisher information term, and that has to do with the gradient of the conditional density with a square, with an expectation, and all these other things. But at least if we start to write down what the gradient of the density looks like, then we can write down something. And I mean, don't look at that too hard. But the important thing is that what shows up is these parameters in my encoder network and the gradient with respect to x. And so I told you very early on with this FGSM method that it's easy to take gradients with respect to x of a loss function of the parameters or whatever you want to do. And this comes when you're training your neural network and things come through backpropagation. OK. The point, though, is that we had two terms, right? So we have a phi term, and then we have another term. And I'll punt on the mutual information framework. But let's imagine for now that it's MMSE. All right, so if the MMSE were there, then I would need to come up with some upper bound of MMSE and use that in my whole machinery of doing stochastic gradient descent and optimizing things. So what's a good upper bound on MMSE? Well, MMSE is minimum mean squared error. Right? So that means that it should be an upper bound for that is any function I can possibly think of that I'm applying to t, and just the mean squared error of that. OK, so the idea in this deep information bottleneck is that I'm going to train another network, and that other network is a decoder network. So basically, the idea is that I have two networks, and they're being trained in parallel. One is extracting these features, which are hopefully getting better and better. And the other is a decoder network that is simple, let's say a logistic regression decoder. That's also being trained in parallel. It's also getting more and more accurate as I'm running this whole process. And importantly, all of these terms well, this is hinted at the calculation I gave you earlier. The gradients of all of these terms come down to gradients of parameters, which are things that I can recover from the neural network. So I think I had a picture of this. It shows up bigger on another slide, but maybe I won't have time to get to that. So the basic idea is that I have my encoder network, right? So I had my x, and from my x, I'm extracting these features, mu and sigma. Those are the means and the covariances. And there's theta is all of the parameters that come into this encoding network. And then I have the decoder, and the decoder is saying that whatever t I got, I'm going to use that to predict the y, right? And the idea is that the loss function, well, the loss function had the MMSE stuff, and it had the phi stuff. So the loss function and its gradients will depend on the parameters of the decoder network, the parameters of the encoder network, and also the gradients of mu and theta with respect to mu and sigma with respect to x. OK. So I'm not going to have time to go through this, so let me just go to here. So then we had some experiments. So I should say this is the part that's really unfinished. So neither of us had any clue how to run TensorFlow. Varun taught himself sometime in the last month and ran some experiments a couple of days ago. So still very much work in progress. So we thought, OK, let's look at synthetic data, and then let's look at MNIST. Because, I mean, I'm told that in the deep learning community, MNIST is not good enough. You need to do ImageNet. But I guess as theoreticians, like, we tried MNIST because it was at least real data. OK, so we go back to our Gaussian case. So our Gaussian case said that we have a Gaussian mixture. And we choose our distribution so that one direction has a much higher variance than the other, so we get these fat pancakes. And then we assume that we're extracting linear features. And so what we want to see is we want to see that if our beta parameter, which is telling us how much we care about robustness, is not there, then we end up with, well, the maximum likelihood solution. OK, so I mean, that should be true regardless of anything I said about information bottleneck. But what we also want to see is that if beta gets bigger, so I care about robustness, then my boundary will tilt from being this one to being something, something kind of standing upright more, like I showed you in one of my earlier slides. OK, so the plots are not really very pretty, but basically this is in fact what happens. So we see that the slope of W, so it went from being sort of the classifier that had the slope that corresponded to this big stretch. So the simulations were 16 to 1, and so we see some sort of a 16 to 1 slope. But then as we crank up beta, then it turns out that this slope will get smaller. So what that corresponds to is that I go from this thing to that classifier. And the other thing that happens is that as beta increases, the magnitude of W decreases. And this is something that I mentioned in an earlier slide as well, which is that the robustness has to do with signal-to-noise ratio. So if you want lots of robustness, you should make W small, because then that will make things really independent. OK, then we looked at MNIST. So MNIST is these handwritten digits. You want to classify into 0, 1, up to 9. And we did something sort of similar. So we said, let's try to extract a two-dimensional feature, and let's see what happens. So really here we had to train an encoder network, train a decoder network. And what we found, and these are preliminary results, is we found that as you increase beta, in fact, there is a bit of a trade-off between accuracy and robustness. And so I say this with an asterisk. So we showed that there was a trade-off in accuracy and robustness in the sense that the accuracy is, in fact, going down as beta is getting bigger. So this is saying we just care about robustness, we don't care about accuracy. So you can show that for your trained classifier, the accuracy is getting worse. On the other hand, you can show that your Fisher information term is getting smaller as beta is getting bigger. Right? So bigger regularization parameter means that the regularizer should be squashed to 0. And if the regularizer is squashed to 0, then things are very robust. All right, so this is as far as we got with the simulations. What I really wish I could show you was some pictures saying, look, now that I did these adversarial attacks on my neural network, and it leads to robustness. And this is the way that things change as I attack my network. But we didn't quite get there yet. I also don't have a visualization yet of what these features look like. So ideally, one can draw what are called saliency maps. So that tells you, if you look at your image, it'll highlight certain portions that are involved in your feature, in your classification. And it would be really nice to say, these are the original features without robustness, and these are the features that it looks like when there is robustness. Like maybe certain curves of the numerals that show up in your image data. OK, so just to wrap up, what we studied was this new robust information bottleneck method for extracting some robust features. We developed the rigorous theory. Actually, this is the only rigorous theory in our work, but this is for the Gaussian setting. And it was a lot of heavy-handed linear algebra, but we showed that, in fact, you can write down, characterize what the solution is, and it makes some sense. We also provided a variational optimization method, which means that you can actually run this on large-scale data. Whether or not it gives you something meaningful, well, the jury is still out on how to interpret whether these features are actually robust. But I do think that the preliminary results are promising. In the future, well, as I said, I would really like to understand if these neural networks are giving you something that's more robust features. So what I've shown you is that the phi term is getting smaller, and I infer from that things are more robust, but we would like to see what the neural network is actually doing. And also, I think, well, this is just sort of scratching the surface of this idea of robust feature extraction. So what does it mean? How do we come up with some alternative methods for extracting the most robust features, or just ranking features in terms of how robust they are? So that's it. Thanks for your attention.